Okay, so last time we stopped with Lab 3. We completed um, Lab 3. Any remaining questions or issues with Lab 3? So now there is an assignment that is due today, and I'm not going to work out the problems in this assignment. That's the difference between a lab and an assignment is I will show you how to do the labs, or give you very clear and comprehensive hints. But for the assignments, those are meant for you to work out more on your own. Try to carry out that problem-solving process without seeing someone else do it first. Are the problem statements for the assignment 1 clear? Are there any questions about assignment 1? I mean, it looks like Lab 3, right, essentially. It's just like the lab. The lab is a warm-up for the assignment. Okay. So let's take a look at Lab 4. And I'm going to just glance at this. The learning objectives. Learn how to use the Boolean data type, learn how to use conditional expressions, and so on. Okay. And that's similar to what went into Lab 3, actually. So let's take a look at the first problem, factoring, and we'll kind of discuss those learning points of learning as we go along. All right, let's look at this. So we ask the user to input a positive integer, and then we compute the prime factors of the number and we print them. And here's an example. The user enters in 100, and the program displays 2255 because those are the prime factors. Right? 2 times 2 times 5 times 5 is 100. And those numbers cannot be broken down to a product of anything smaller than themselves. That's clear, right? If I gave you another example, you would be able to come up with the prime factors. Say like 99. What are the prime factors of 99? How many prime factors into 99? What are the 3? What? 3, 3, and 11. Yeah, I mean, you just start. Let's see, one way to do that. How do we do that? Just think about how did you calculate the prime factors of 99? Well, let's see. We'll try to divide by 2. No, that didn't work. Let's divide by 3. Does 3 go into 99? Oh, yeah, it does. So it leaves 33 left over. Now let's try 3 again. Oh, yeah, 3 goes into 33. So we have 3, 3, and we have 11 left over. Can we break down 11? No, 11 is a prime number. How do we know that 11 is a prime number? Because 2 doesn't divide into it, 3 doesn't, 4 does. Well, we don't have to check 4. 5 and 7. That's it. Those are the prime numbers. They don't divide into 11. So 11 is prime. Develop 8 test cases and verify that your program runs correctly for them. The test cases should contain some prime numbers as well as non-prime values. Include the test cases within a multi-line comment in your code. Make sure the comment is nicely organized and easy to read and understand. All right, let's do this. Do you want me to use, do you want me to SSH to Lab Machine and work there, or do you want me to work in Visual Studio? How many for SSH? Okay, that's the winner. All right. I'll make a folder for this. It's Lab 041. Let's first build a hello program. All right, this line here, that's just for, I put that in there only for Visual Studio. We don't need that. Because in Visual Studio, the console window is shut down when the program terminates. But on the command line, the way we're working now, the console is just there. It stays open. All right, let's build that. And you can see that a.out was generated. There's our hello program. All right, let's just start solving it the way we mentally figured it out. How we did 99. We started at, we started at 2 and tried to divide it into 99. And we did some looping until we couldn't go any farther. So let's try to figure out how to code that up, how to code out that looping process, starting at 2, then trying 3, then 4, then 5, like that. Actually, I'm not sure right now how to solve the problem. Is that we didn't cover functions yet. Do we cover functions in the assignment, in the reading, right? So we've only gone to chapter 3. Is that right? Okay. All right, let's so here we have n. Just do something like this. We don't need the return 0. The compiler puts it in there, but I'll just be explicit about it. Oops. What's the problem here? What's that? Oh, down here. Oh, yeah. All right, let's just clean that up a little bit. Okay, so we have the shell of a solution here. Now we need to create the algorithm. So let's think about how we're going to do this. So we have a number, say n, and what we want to do is try to continue to divide that number. Let's do. I'm just gonna, wouldn't just note this down, okay? This is just like a first guess here. It's probably going to look completely different when we're done. So let's think about it. One of the learning objectives was to learn about using Boolean variables. It's a variable that represents true or false. Let's just go ahead and create one. I'm going to call it done. We'll set it to false. Okay, it's the process. We're trying to solve a problem. Are we done? No, done is false. And then when we're done, we'll set done to true. Probably we're going to take that out. I'm just thinking out loud how to do this because, I didn't prepare to do this problem today. I think you can finish this with the material that we were given so far. I think we can do it. There's easier ways to do it if we have functions, but we can do it with the machinery that we have right now. So while we're not done, let's do something. Maybe something like try the next factor. You know what? The color doesn't work, does it? Let me fix that. Where do I go here? Change settings. Try the next factor. Once again, like I said, I haven't thought about this problem. I didn't prepare for the class today, so we're really going to figure this out together. Try the next factor. So that means we have something like a factor. Let's define a factor. Let's set it equal to 2. And then we'll do something like this. We'll do our number n, and then we'll do mod 2. So that means take n, divide by 2, and give me the remainder. So if n is 3, 3 mod 2, it's like, 3 divided by 2, and then give me the remainder. Oh, that's 1. So n mod 2, 3 mod 2 is 1. So the remainder is this. N mod 2 gives a remainder after dividing by 2. I don't want to divide by 2. I'm sorry. I want to divide by what? F. That's the factor. Right? So if the factor is 5, we do n, and n is 10. And then we go 10 divided by 5. That'll give us 0. The remainder is 0. So that means 5 is a factor of 10. All right. So if the remainder is 0, then we found a factor. We found a factor. Hurrah. So let's print it. And after we print the factor, let's print a space. In fact, this line here, the prime factors are, we need to put that up here before the loop. So we want to enter into this loop. So first we print the prime factors are, then we enter into this loop where we're trying different factors and printing them out as we find them. Okay. Then, but let's suppose, all right, let's suppose we get the factor and we print it out. At that point, we have to take the number out. We have to take it out of this running total n. So we're going to take out that factor f. So once again, if n is, say if n is 9, and f is 3, let's figure that out. Let's think about that. Let's suppose that n is 9 and f is 3 at this point in the loop. then 9 mod 3 is 0. If remainder equals 0, yeah, that's true, remainder is 0. Then print f, so that means we print 3. And then we take n, which is 9, and we divide it by 3 to give 3. So now n has been reduced to 3. And then we come back up here again in our loop. And now f is 3 and n is 3. The remainder is 0. So we're going to print 3 again. And now we set n to 1. If we continue the loop, what happens if we continue the loop? Actually, what happens if we type in 9 right now? Actually, we're not incrementing f, are we? Let's suppose we input the number 11 for n, and f is 3. So we take 11 mod 3. What's 11 mod 3? 2. So the remainder is not 0. So we need to try the next factor. So we want to try the next prime factor, but we're just going to increment f right now. So here's the loop. We initialize f to 2. And if f turns out to divide into n nicely, then we take f out of n. But if f doesn't divide into n nicely, then let's forget about f and move on. Try the next f. So we're going to increment f. And then we do the whole process all over again. And we're going to do that until we're done. Well, this is where we reduce n. And if n is reduced to if n is reduced to 1, then we're done. It's still not there. I'm sure it's not there, because actually we're looking at non-prime numbers. I don't know if that's going to mess us up or not. It's like, so if we start f at 2, and then we do, and then we go to 3. Well, 3 is a prime number. And then when we go to 4, is that going to mess us up? No, I don't think it will, because a 4 is we've already taken out all the 2's, so that means 4 cannot be a factor. I think this is pretty close to the solution. Are we at a point to test this? I am not fully confident, okay, that this is the solution. Do we want to think through it again mentally? Test it mentally? Run it mentally? Or do we want to test it using the computer? Let's test it mentally. Actually, this is let's do our test cases. That's it, because the problem asks for test cases. So I asked for a comment, a multi-line comment. Look at that. VI puts that in there. And these are the test cases. And so we'll have a column. This will be the input. And this will be the output. All right, we're going to do manual testing. Later on, we'll do automated testing, where we write the test itself will be built right into the code. This time, we're just going to look at our test cases and try them manually. All right, let's. So it should be. The program takes a positive number. So what should be the output? If we type in 1, we want 1, right? That's a special case. If we type in 2, then we want 2. 3 should give us 3. This is our first non-prime number. Well, 1 is not a prime number. Is 1 a prime number? Yeah, 1's a prime number, of course. Yeah, 1's a prime number. And 4 should give us 2, 2. 5 is going to give us 5. 6 is going to give us 2, 3. I'll accept 3, 2, but I'm thinking that we start at 2 and we go up. I think if you start on the top and go down, that's not going to work, because 8, you're going to find 4. If you start at 8, you went to 7 and 6, like that, and then when you hit 4, you're going to say, oh, 4 is a factor of 8, but it's not a prime factor, so we want to start at the bottom. We want to get 2. We want to pull the 2's out first before we try the 4. So we're on the lower numbers. We're going to try some big numbers, but let's see if we can get it to work for the little numbers. Now, the one I want to temporarily ignore is 1, especially. That's a very special case, and 2 is kind of a special case too. Those are called border. What do they call them? Border cases. You've got an algorithm you're developing. You've got special cases that are unique. They start somewhere. They're on the edge. Something like that. So this is the starting point. 1 and 2 are special cases. Especially 1. Maybe 2 is not. All right, let's try 2. Let's try 2. Let's try this case. Just that one case. All right. The user types in a 2. N is equal to 2. We set F to 2. N is 2, F is 2. We set done to false. So we're going to do, well, not done, that's true. We compute the remainder, 2 mod 2. That's 0. Remainder is 0. The remainder is 0. Okay, we found a factor. We're going to print 2. And then we're going to take 2 divided by 2 and store the result in n. So n gets 1. If n is 1, then done is true. And we don't do the else because we did this part of the if statement. And we come to the bottom of the loop. Well, that means we have to go back to the top. And what do we do here? We evaluate the condition while not done. Well, done is false. I'm sorry, done is true. Done is true. And so not done is false. So that means the condition for the while loop is now false. That means we no longer do the loop. So execution goes to the next statement following the body of the loop. We print n. Well, that's not right. Right? That's our junk code. We left it in there. We just want to print a new line. So I think it's going to work. So I went through it mentally. I tested it mentally. Any discussion on this before we try it? Back there? If I try 1? Yeah. No, let's not jump ahead. I just want to do the test case 2, okay? So yeah, let's do that next. Okay, let's put that aside. I'm going to just check the logic for just this one test case right now. Let's not try to do everything all at once. Incremental development. Well, that's why I warned everybody about one, right? So those border cases are really tricky. Enter a number, 2. The prime factors are 2. It worked. I say we delay this. Oh, 1 is not prime. 1 is not prime. What's the definition of a prime number? A number that whose only factors are itself and 1, right? Yeah. So I think 1 is prime. Isn't it? Oh, a prime number must have 2 different factors. I mean, what does it matter? I mean, it's just a matter of, what do they say in the movies? Oh, now we're talking syntax, Dr. Watson. So, whatever. Right? Semantics, sorry, not syntax. Now we're just talking semantics. I'm thinking of a video game I played. It was that one that goes where Assassin's Creed. Remember that line? Do you remember that line? Does anyone play that game? The first one. Anyway, I got a better memory than you guys. Huh? All right. Let's try 3. And 1 is a very special case, so let's delay on that one. Let's try 3. So n is 3, f is 2, done is false. We take 3, we divide by 2, the remainder is 1. Am I going too fast? All right, n is 3, f is 2, 3 divided by 2, and take the remainder, we get 1. So if remainder, this is not true. Remainder is not 0. So we do the else block. And we increment f. So f is now no longer 2, it's now 3. And we hit the bottom of the loop. That means we come back to here, and we test the condition. Well, done is false. We're not done. So not done is true. So now the condition for the while loop is true. That means we do the loop. And now we have 3 mod 3. The remainder is 0. This is true. We print 3. And then we take n, which is 3, divide by 3. That gives us 1. This is now true. We set done to true. Wait, 1 is always a prime factor, right? Is 1 a prime factor? Do we want to list 1? Like, should the output here, should the output for this be 1 and 2? So we're not going to accept 1 as an input then. Is that fair? So let's solve the problem of a funny 1 like this. If n is less than 2, then we'll say bad number. Enter a number, enter an integer larger than 1. So we'll call that a user error. What do we do now? How about this? Let's just get out of there. Let's do this. Enter a positive integer to factor. We won't tell the user about 1. All right, let's test. So actually, we've handled 1. We've handled 1, and we should test it. All right, that works. So we've tested 1 and 2, and then 3. We went through 3 already. It looks good, right? So 3 should work. 3 works. Do we just try 4, or do we mentally go through it? Who wants to just try 4? Who wants to mentally go through it? It worked. Incredible. That's incredible. What about, we better test the other cases, right? So 5, 6, 7, 8 works. 2, 2, 2. I'm getting more confident now. How about 9? Whoops. Looks good. How about 27? Looks pretty good. How about, you know what? We're getting out of control. We tried 9. Oh, 8 was important. 8 was the first number that gave us an output of 3 numbers. And then we tried 27. Did we try 27? Yeah. That worked. All right, let's try to break it. What's a number that can break it? I mean, you know, not a negative number. I mean, we could try that, but just we want to get an error message. 37. What's the output going to be? 37. Huh? 8? Oh, I forgot to do 8 start, right. Thank you. All right. Well, we didn't change the code, so we'll just try that. 37. Incredible. That works. Is there anybody who's not convinced that we solved the problem? Yeah. Why did the loop continue? Yeah, like 1, 2 to 3, and then it went down to L and didn't complete that. Okay, let's start the story from this line right here. What is N? 3. What is F? 2. Okay. So N is 3 and F is 2. Let's try that. So this is we're going to mentally test that state right there. Okay, so we come to here. What is the remainder? 1. The remainder is 1. Let me do it like this. Remainder is, well, no, we can remember that, right? The remainder is 1. So that means we do this. We take 1 and we compare it to 0. 1 is not 0. That means this expression here, that expression is false. That means we do not do what's in the body of this, the first body of the if statement. We do what's in the second body, which is just one line, one statement. So we take f and we add 1 to f. F is 2, so let's add 1. That gives us 3. So the 3 that we get, this expression here evaluates to 3. The 3 is then stored into f. So now f becomes 3. You got it? And then when we hit the bottom, this is, a lot of people get stuck here, okay? So I'm going to keep talking. What happens when you hit the bottom? You come right back up on top, just like the American economy, right? And then what do we do when we come back to the top? We check the loop condition. We haven't altered done. Done is still false. So not done is true. And so that means we continue with the loop. Any other questions? So I'm trying to show you the process, how to devise an algorithm to solve a computing problem. Yeah.
Is it possible to do this with negative exponent?
With a negative exponent?
Yeah, like the equivalent of the square root, and then if it has a remainder, like the percent sign, then you could say it's n for whatever the inputted number.
Yeah.
Would that work?
Could you use it like an exponent? Still not sure. You mean like take?
Well, 107, the square root of 107 has.
Oh, this is a different problem, right? Like computing the square root of a number?
Yeah, it's the same thing, it's just we're not using division.
Give me an example.
Like, okay, 107.
Okay.
If you take the square root,
Yeah.
which is like up caret, I guess, 1/2.
Okay.
It has a decimal number,
Yeah.
and 107 is prime.
Right.
So if that decimal is present, which would be the percent sign,
Yeah.
it would just be the inputted number. So you create a variable for the input, which actually.
So what? Yeah.
So n would, the output would equal n.
So you're taking but you're looking for. So that's the numbers that have even square roots, right? But I don't think that works for 9, right? But what about 11? I don't understand the proposition actually. So if you take the square root of a number, or you take the nth root of a number, is that what you're doing? The nth root, and n equals 2, and then 3, then 4, then 5, like that? Because see, if you take the square root of 9, you get 3, right? Huh?
Yeah, it would be 3.
But if you take the square root of 11, then you'll get a decimal value. But 11 is prime, right? I don't understand the theory there. But there's definitely other algorithms that will solve the problem. And I think what you're going down is excellent, and I encourage you to continue to process that possibility and do that investigation. I think that would be good for you, especially if you're a math major, and see where it goes. And then you'll learn more about number theory and everything actually. So. And then you're going to need to develop your definitions and be precise and try to code it up, generate the test cases. I think there certainly are alternative algorithms for resolving the problem. And actually, if you come up with an alternative, tell me. And if you want to talk to me after class about it, I'll do that too. I don't want to spend too much time on it. Okay, move on to the next problem. So it's lab 4. Write a console program that reads a positive integer entered by the user. So that's the same thing. It's the same input. The program computes and displays all the prime numbers between 2 and the number entered. To solve this problem, you need to nest an inner loop within an outer loop. So I give you a hint there. So one of the reasons for this problem is to learn about nested loops. All right, let's do that one. I'm just going to copy over the main. It's very similar. So it's very similar. So once again, the user enters a number, positive, enter a positive integer. If it's less than 2, we'll say it's a bad number. And we want to print the we want to say something like the prime numbers less than or equal to n is like that, right? This doesn't work, but let's just try. Let's make sure that the user input part of it is correct. So enter a positive integer 100. The prime numbers less than or equal to 100. Ooh, is. Let's call that R, right? All right. So all right. Let's develop our test cases. So if we type in 2, and then 2 is the correct value, right? If we type in 3, we should get 2 and 3. If we type in 4, we should get 2 and 3. 5, 2, 3, and 5. Is that right? Am I getting this? Eight. So type in a number, then give me all the prime numbers between 2 and the number you typed in. We should have do we need a bigger number? Give me a bigger number. 25. 25. 19. And this is the point where, when we run the program, we're going to doubt our test code, our test case, rather than doubting the code itself, right? Okay. All right, let's try this. So, I think this is an easier problem than the other one. I should have put them in the other sequence, maybe. So let's use that Boolean done value again. We'll start by trying 2. And now let's do this differently. Maybe we'll try a for loop here. Actually, this problem is much easier. I mean, my idea is just to try every number that's less than the number that we typed in. There might be more efficient ways of doing it. And we'll try, we'll use I because that's a typical index in a loop. So we'll start at 2. And while I is less than or equal to the number, if I is prime, then print it. This is it, right? Isn't that the whole problem right there? That's going to solve the problem. So we type in n, and then we start with 2. We say is 2 less than n, right? So if then we say if we have to decide is 2 prime. If it is, then print it. Okay, let's increment I. Now I is 3. Is 3 prime? Oh yes, it is printed. Increment I. Now I is 4. Is 4 prime? No. So all we need is a way to decide whether I is prime or not. Yeah, we'll use that remainder operator. So we'll do I mod. Oh, I'm sorry. If I is prime, how do we know if I is prime?
If it has a remainder.
Wait, this is not easier than the other one. This is not at all easier than the other one. I don't know what I was thinking. All right, I is the candidate prime number. How do we determine if I is prime? Use the remainder, right? Yeah. How do we use the remainder? Let's say I right now. We have an I. What do we do with the I? Remember the hint. Say that again?
Divided by the f factors that you have.
All the f factors. Let's call it. Let's call it. Instead of the I, let's call this. Let's call this. Yeah, I guess I is all right. Let's use the index f. So f is a factor. So we want to know if I is prime. So let's try to divide in that. If I is prime, that means 2 doesn't divide into it, 3 doesn't divide into it, 4 doesn't divide into it. All the numbers less than I does not divide into I, right? If we knew that every number, if we tried to divide a number into I that was less than I, and it always gave non-zero, then we know that I is prime. Is that right? So once again, we're inside this. We're trying every I between 0 and n. We want to know for each one of those i's, are each one of those i's prime or not prime? If it's prime, I'm going to print it. If it's not prime, I'm not going to print it. That's the outer loop. The outer loop. Try every number between 2 and the number that the user entered, n. And for each of those numbers I, we're going to iterate through all of the numbers less than I and try to divide them into I to see if we get a 0. Because if we get a 0, we know that I is not prime. Because a number less than it is one of its factors. So if the remainder is not 0, no, this one is definitely harder than the other one. So we know that I is not prime. Let's use, there are many different ways of doing this. I'm going to use a technique which I think is the easiest for you to understand, and that's to use a Boolean variable. Here it is. We've got an I. We've got an I. We want to know if I is prime or not. And let's assume that I is prime. I is prime. How am I going to write that out? I is prime. I'm going to say is prime is true. But I want to say I is prime is true, but I can't write that very nicely, can I? I is prime. How about I do it like that? I is prime. Oop, got a space in there. I is prime. Let's assume that I is prime. That means we're going to print it. And look at this loop right here, okay? This loop here, at the end of this loop, we said that I was prime, and then we're at the bottom of the loop, we're going to do this. If I is prime, then we're going to print it. I is prime. But so that means this loop, what this loop is all about, we're going to assume I is prime. And then what the loop is going to do is going to see if it finds the factor, if we can find a factor, we're going to set I is prime to false so that we don't print I. Right?
Just a math question. If there is a remainder,
Yeah.
doesn't that mean I is prime?
If there is a remainder. No, but if there is a remainder for every integer less than I, not just for a given integer. That's the thing. If the remainder is 0 for any integer, I is not prime. So that's what we're going for. Yeah.
So prime I, you just have I divided by itself. Then if the remainder is 1, then we know it's prime.
I divided by itself will always be 1, right?
Yeah, but up that case, before it divided by itself, it needs to divide any number smaller than it.
Yeah.
Way down to 2.
We don't need to check whether I can be divided by itself. That's true for every I. So we are only going to look for numbers less than I. If any number less than I divides into I, gives us a remainder of 0, we know that I can be factored and it's not prime. Is that right? Okay. Now the logic in here isn't right. We've got to look at this logic here. We're going to do the remainder. If the remainder is 0, so we don't care about whether it's not prime. I mean, actually at this point here, we don't care whether the remainder is non-zero. If the remainder is non-zero, we just got to check the next f. The case we're looking for is when the remainder is 0. Then we know, our assumption that I is prime, which we made up here with this Boolean variable, if we find a non-zero remainder, we got to change that assumption before we get down to the condition that's going to trigger the printing. Is that it? Did we get it? See, what you need to do in this problem is you've got this outer loop, and you kind of have to forget about it for a little while and just focus on the inner loop. The outer loop is just ranging across, starting at 2 and going to 3 and then 4 and then 5 and going up to n, whatever you typed in. So the whole purpose of the outer loop is to generate a bunch of i's. Now, once you have an I, so we can forget about the outer loop. Let's just say we've got an I. Okay, we have an I. I don't care about ranging through all the values. We've got some I now. Now we just focus on what I have highlighted there. Okay, how do we decide that I is prime or not prime? Well, let's start by assuming it's prime, and then try to find something that divides into it. And if we find something that divides into it, then let's reverse our assumption. And then at the end of that process, that loop, at the end of the loop, we're going to check whether our original assumption is still true or not. If it's still true, I is prime. That means if I turns out to be true here, that means we never found a remainder that was 0. Oops, need 2 of those. Is that going to work? I can't see. I can't look at it. Oh, that worked. That looks good. Oops, sorry. It's hard to read the thing, isn't it? What are our test cases again? We went up to 8. Let's try 8, and then let's do 25. Now we're done. The 8 looks good. And 25. At this point, I'm checking the test code. Right? Okay, that's it for both problems in the lab. And that's it. We'll see you next time.
Can you go back to the code?
What's that?